Determine the tension in the cable and the horizontal and vertical components of the reaction of the pin A. The pulley at D is frictionless and the cylinder weighs 80 pounds. Okay, we have a really unusual, weird looking problem today where we have a beam, a weightless, massless, frictionless, widthless, everythingless beam. And we have a pulley with two strings attached to the top. So it's really interesting, and we'll break that down with our equations of equilibrium a little later. But as always, we're going to start with the fine variables, I should say. So we have tension, and we have AX and AY. Okay, so let's start with the free body diagram. As always, a big beam and start dimensioning it. We have point A right here, point B, an unlabeled point, and point C right here. Okay, let's start looking at our forces right here. So we have AY, and we're going to have AX right here. Again, because there's a pin joint right here at A, it's not going to resist any moments. The beam is free to rotate around A, but it does resist forces in the X and Y directions. Okay, and then at B right here, we're going to have tension pulling upward right here, T, and we have the same tension force, but at an angle right here. So that's going to be T again, but it's going to be at with a 1, 2, root 5 triangle, I guess. Root 5 triangle. We just get that root 5 by taking the Pythagorean theorem of 1 and 2. Okay? And then at point C right here, we have an 80-pound mass acting at point C. Okay? And the dimensions of 5 feet split up into 3 sections, so everything's nice and evenly distributed right here. 5 feet. And that's all for the free body diagram. Okay, so let's move on to the equations of equilibrium. Okay. So of course we're assuming this whole beam is at rest. Let's start by summing the moments about A. So equal to 0. This way we'll only have one unknown in our equation. It will be T. So let's write it out. About A, and then the force at A create a moment. There's no moment arm for either of them. So next one we'll have is force T. This is going to be a positive moment, and it's going to be acting 5 feet from point A. Again, we're going to have force T. We're going to find the component of this T because it's angled. We're going to take 2 over root 5. So just like any other, usually we see a 3, 4, 5 triangle right here. But we're going to take, if you'd like had just this triangle, to find this component given this triangle, given the side length 5, it would simply be 2 over 5, and you should get the length of that. Okay, I should say the ratio between the hypotenuse and the vertical component, not that side length. The side length here is 2, and get the ratio between the hypotenuse and the vertical component is going to be the same ratio between the vertical component of the tension and the total tension. Okay, and we're simply finding the component because only the vertical component will be creating a moment. The horizontal component will have no moment arm and thus not creating a moment. Okay, and it's be acting at 10 feet from point A. And then again, a positive moment for that using the right-hand rule. And I'm going to have a negative 80-pound force acting at C. It's going to be 15 feet from point A. I'm going to set that all equal to 0. Actually, sorry, I did not mention this correctly. This is 3 feet That's kind of embarrassing. We have 3 feet acting there, and that's going to be 13 feet. Let's caught that. Sorry about that, folks. 3 feet. It's important to be careful with all your dimensions and all your units and everything, of course. Okay, and that's going to be a negative moment because acting in the clockwise direction versus tension acting in the clockwise direction, counterclockwise direction. And yeah, if you plug this all into a calculator and solve for t, you should find t is equal to 74.6 pounds. And that's going to be our first find variable, 74.6 pounds. And that should make it relatively easy to solve for the rest of the unknowns. So we're going to sum the forces in the x direction. When we have 2 forces acting in the x direction, we have ax, it's going to be positive because it's going towards the right. And we have negative tension to find the horizontal component. Tension is 74 points. To find the horizontal component, I'm going to take 1 over root 5. 1 over root 5. And again, that's just going to be the ratio between the hypotenuse and the horizontal component. So if that ratio is the same, that would be the relation between the horizontal component of the tension to the total magnitude of tension. Okay, and then set it equal to 0, because of course at rest you should find AX is equal to 33.4 pounds, and that will be our second unknown today. 33.4 pounds. Okay, and then for our last unknown, our last equation, sum the forces of y and set it equal to 0. Okay, so we have AY, check the sign would define that. AY is going to be negative here. Okay, it's kind of arbitrary. I'm taking the guess that the reaction at y is being acting downward to kind of balance out the moment created by the 80 pounds right here and the two tensions up here. Again, if we got a negative answer for it, we know that we just flipped the arrow. We assumed the arrow is in the wrong direction. But I think it's going to be down here for this one. So take AY. Next we have tension force going upwards here. 74.6 pounds. That's going to be the full vertical tension right here. And we have the component right here. I'm just going to find the vertical component. So it's going to be the same. 2 over root 5 for that. 24.6 pounds. Okay. And then we have that 80 pounds going in the negative direction there, pulling it down, pulling the beam down. Set that all equal to 0. And you should find that AY is equal to 61.3 pounds. And that's going to be a third and final unknown for this equation here today. A third and final unknown for this problem here today. And this is the confusing little double rope tension problem right here. Really not that bad once you break it down. Just once you got to remember that tension's going to be equal here to keep everything at rest. And that's it. We're done.